Okay, class. Now we're in Chapter 12. We're going to go ahead and do paired confidence intervals and hypothesis tests. This is the two sample case where they are paired. We'll use the Whitlock and Schluter example of testosterone levels in blackbirds. It's on page 282 of the text. Okay, you can pause and read it if you want to. The issue is we've got a sample of 13 male blackbirds, and the hypothesis is that if we give them testosterone, then it's going to give them more sort of mating success, but they'll be less healthy. So we're going to measure that by looking at their immunocompetence levels. So the way we're going to do that is we'll just take a look at the data. You've got the data loaded, so I'm going to click on blackbird testosterone, and this is the immunocompetence level beforehand. The units are given. The only thing we need to know about it is that it's not normally distributed. Taking the log gives us approximate normal distribution. So befores and afters, and the logs are popped in there. What I'm going to do, I hit the up arrow, and then I hit my home key, and I'll do the attach command, is I want to look at those befores. There they are. If I take the log, just do log before, then that gives me the same exact results as is already given in the data set. So nothing mysterious there. Take note that this is natural log as the default. If you wanted the log base 10, then log 10 is the correct command. Before we analyze the data, it's always a good idea to just take a look visually at what's going on. We have these log before and log after values, and by eyeball they look somewhat similar. So what we want to do is, and I've got these scripts in the Whitlock-Schluter text examples file, go ahead and do some basic descriptive statistics using just starting with graphs. So let's get a box plot of these guys. Box plot command, I'm putting the log before and the log after in. It's a generic looking plot. We can see what's going on. I like to add, let's get some names here on the x-axis and attach a title. Now we've got the antibody levels before and after. Clearly after the antibody levels are higher, they were predicting lower. But are they statistically significantly higher? We'll need to check that in the test. Okay, so since I've attached, I can access log dot before and log dot after. So what we're really interested in is the difference between those two guys. So log dot before minus log dot after, and I got those. Notice it's called up here diff in logs. That's really the thing I'm interested in. How many are there? Well, it said in the notes that it was 13. We can count it right here. Sure enough, it is 13, so everything's looking good. Now, I want it to be very clear that at this point, this is just a Chapter 11 confidence interval. We're going to use these observations. It's a random sample, and they're approximately normally distributed, so we'll just do a T confidence interval. That's it. We can take the mean diff in. We can take the standard deviation, and then of course divide that by the square of the sample size, and I've got my numbers that I need. So we'll take those numbers and let's go for it. Here's that mean that we had, mean difference. Notice I've got x bar difference. Standard deviation is what we got, standard error. There it is. So what we like to do next is sketch our diagram. I'm just going to go ahead and go like this. Minus 0.0, let's just say 5, 6, and we're looking for a margin of error. So the t, we're going to use a 95% confidence interval. So 0.05, 2. What's the degrees of freedom? We're going to use 13 minus 1, which is 12 again. Now this could be a point of confusion because there are 2 samples, but as I said, this is just like we're using a single sample of size 13 because we're doing differences, not the 2 independent groups. They are dependent upon one another. So we pop over to our table and pull out the appropriate t-stat. This is our t-table. Okay, t-distribution. Just wanted to make sure I wasn't on the chi-squared. So there's my 12 degrees of freedom. 2.18 is my number. 2.18. E, therefore, is going to be 2.18 times 0.0441 from up here. And I've got 0.096, which is about 0.1. And so doing the calculations, that's going to take us to about 0.040 at the top, minus 0.152 at the bottom. So the interval contains 0 somewhere around here. Is my 0. And let's just label this thing a little bit better here. This is my x bar diff level, and yeah, we could have a z-score. All right, so 95% confident. The true mean difference is somewhere in there. It includes 0. We could have higher immunocompetence before, higher immunocompetence after. We're not sure. Therefore, we're not detecting any difference of the added testosterone. It doesn't appear to weaken the immune system, at least at the 95% confidence level. Okay, as you can tell. Now, what if we wanted to cash that out as a hypothesis test? What would be different? Frankly, there is a clear relationship, and formally, there's a thing called a duality between confidence intervals and hypothesis tests. We're not going to get into details of that this semester. You can see how it works with the t-stats. But 4 steps of hypothesis test. Null hypothesis is mean difference is 0, and the alternative, mean difference, is not equal to 0. Oh, we got a typo here. Okay, you can tell that's going to be copied from above. Okay, the stats are the same as we had before, so what's of interest is the test statistic in the diagram. Let's do the diagram over here. Same looking bell curve, but its center is different than the confidence interval center, okay, which was at the statistic. For hypothesis tests, the center is always at the assumed value from the null. So this is the null distribution. The center is at 0. So we're looking at x bar diff assumed to be at 0. And we're interested in the t-scores. So the test statistic is t equals, as always, we do the statistic minus the parameter over standard error. That's always the form for a t or a z. Our statistic is the difference. So minus 0.056 minus, the parameter is assumed to be 0. That comes from the null hypothesis. So pop in the 0, standard error over here, 0.0441, and that number is minus 1.27. Okay, that's our t-stat. So the difference is minus 0.056. At the t level, that's, you could think of it as 1.27 standard errors below the mean. Now, we don't have a specific p-value, so what we tended to do was use absolute value of the t-stat, and we compare less than or equal to sorry about that. We'll have our absolute value of t less than or equal to the critical value, t.052. And so we had 1.27 less than or equal to 2.18 was the number we got from the previous problem. And so when we go less than, that implies do not reject. Do not reject the null hypothesis. This is a big old p-value. We'll show how to get it in a sec. So that's a p-value. Okay. The 2.18, let me put that one on. That's the guy that is going to separate me, 2.18, where I would have that 5% cutoff level we would reject. Okay, but ours is much larger. Okay, now in R, if I wanted to get that p-value, what we would do is, let's just start off with PT, that's cumulative probability distribution for students T, negative 1.27, parameters degrees of freedom 12. Okay, that gets me 11%, and that is on the left-hand tail. Since we're doing a two-tailed test, I'm going to multiply by 2, so we should have a p-value of 0.23 roughly. Okay, that'll cover it, and I can pop that on. But what I'd also like to do is show how to do this on R. If we do t-test on log before, log after, using paired equals true, need that parameter. It's defaulted to not be paired. Then it's going to give us the paired t-test with results forthcoming. And so notice the p-value there. We had the 0.23. We matched that. Degrees of freedom, t-statistic. We're good to go. Okay, what I'd also like to demonstrate is one more approach. This one I will do on R. We had log before minus log dot after. Let's go home. Just call that D for difference. Okay. If I just do the t.test on D alone, then I'm going to get the same output. Okay, that's because it's treating it as a one sample test, but remember I said that's what it was, just on the differences. So these are mathematically equivalent, as you can see. And that covers our paired t-test.